that is at rest, and it's being released, and it has an constant acceleration of 2.6 radians per second, and we're looking at it over a time period of 6 seconds. So the first thing that we're trying to find is the angular speed. We know what we know. We don't know the angular speed. We do know that the angular velocity at rest is 0. The angular acceleration is 2.6 radians per second squared, and time interval is 6 seconds. So what we're doing is we're using the equation angular velocity equal to the initial angular velocity plus acceleration times delta, the change in time. Because we know that the wheel starts at rest, we go ahead and cancel out our initial angular velocity, and we get angular velocity equals to acceleration times delta t. And so what we do is we multiply 2.6 radians per second squared times 6 seconds, and we get that the angular speed is 15.6 radians per second. I also, in this problem, looked to see what the angle of the wheel was as it turned. Once again, what we know is that the initial angular velocity is 0, the angular acceleration is 2.6 radians per second squared, and t equals 6 seconds. What we have is to find the angle of the wheel, we use the equation change in theta equal to the initial angular velocity times delta t plus 1/2 acceleration time squared. Because we know that the angular velocity initially is at 0, we can cancel this out, which allows us to then cancel out the change in times, because 0 times any number is 0, which leaves us with the equation delta theta equals 1/2 acceleration times time squared. So if you put in the equation 1/2 times 2.6 times 6 squared, you get that delta theta equals 46.8 radians. Like I said, this is my reassessment for rotational dynamics.